The Bitcoin blockchain just crossed roughly 700 gigabytes, and it's been putting on weight fast, more than doubling in size since 2021. Some researchers project it could push past a terabyte before the next decade is out. That sounds like a technical footnote. It isn't. Because the bigger that ledger gets, the harder it becomes for an ordinary person to run a full copy of it. And the network was never supposed to depend on a handful of giant companies to keep it honest. This is what engineers call the blockchain trilemma. And it's the central tension this entire technology has to solve to survive its own success. Welcome back, and thanks for joining us for part 2. In our last episode, we traced blockchain back to a 1990s newspaper ad and opened one up to show you exactly how it works. If you're new here and jumping straight into this one, no worries, you'll still follow everything, though part 1 is worth a watch for the origin story. Today, we're looking forward. We're going to explain why crypto mining has quietly turned into a capital-intensive infrastructure business, why Layer 2 systems are the only realistic way to keep this network from buckling under its own weight, and how artificial intelligence, right now in 2026, is starting to use blockchain to prove it isn't lying to you. In this episode, you'll learn how techniques like sharding and rollups let a blockchain handle enormous transaction volume without handing control to a handful of players. We'll break down the brutal, unsentimental economics of Bitcoin mining in 2026, where efficiency, not enthusiasm, is the only thing that keeps a mining operation alive. And we'll close on the piece nobody saw coming a few years ago: AI agents that now carry their own crypto wallets and pay each other in real time without a human clicking approve. There's no hard rule that stops a blockchain from growing forever, but in practice, it runs straight into physical limits. That's the trilemma. You can optimize for security, scalability, or decentralization. But pushing hard on any two tends to weaken the third. Start with storage. Every new transaction adds permanent weight to the ledger. If running a full node, a complete copy of the entire chain, gets too expensive or too slow, ordinary participants get priced out. And when only large, well-funded operators can afford to run nodes, you've quietly recreated the very centralization blockchain was built to eliminate. Then there's bandwidth. Bigger blocks take longer to propagate across a global network of computers. That lag can cause forks, the chain briefly splitting into competing versions before the network sorts out which one wins. The industry's answer isn't to keep brute forcing the base chain bigger. It's to build up and out. Layer 2 systems, things like the Lightning Network or a newer approach called rollups, handle the bulk of everyday activity off the main chain and only settle a compressed summary back onto it. Think of the base blockchain less like a daily notebook and more like a bank vault. You don't want to reopen it for every single transaction. You want it opened rarely for the transactions that really need that level of security. So how do you actually make that work at scale? That's where a technique called sharding comes in. Imagine a massive filing system, and instead of one office processing every single request in line, you split it into a dozen smaller offices, each handling its own slice of the workload in parallel. That's sharding. Instead of every node processing every transaction on the entire network, each shard only has to process its own portion of the data. The payoff is real throughput. Researchers combining sharding with trusted hardware environments have demonstrated transaction speeds in realistic test conditions that start to approach what a payment network like Visa handles on an ordinary day, a scale that would have sounded like science fiction for a blockchain a decade ago. That's the scaling side solved, at least in principle. But scaling doesn't mean much if the people actually running the network, the miners, can't afford to stick around. And in 2026, staying in that business looks nothing like it did even 5 years ago. Bitcoin mining used to have a hobbyist streak, someone with a decent GPU, chasing a little extra income on the side. That era is long gone. In 2026, mining is a capital-intensive infrastructure business, closer to running a power plant than running a computer. Here's why. Bitcoin's block reward, the payout miners earn for confirming transactions, is cut in half automatically every 4 years, a built-in feature called the halving. It dropped to 3.125 BTC per block back in 2024. The next halving, in 2028, will cut that again, down to 1.5625 BTC. Every 4 years, the same operation has to do the same work for half the reward. That means profitability now comes down almost entirely to two brutal variables: electricity cost and hardware efficiency. Operations paying more than roughly 10 cents a kilowatt hour are increasingly getting squeezed out entirely, which is exactly why the industry has undergone a real shift toward renewable and low-carbon energy. Not out of idealism, but out of necessity. Independent research now puts more than half of all Bitcoin mining's electricity on sustainable sources, largely hydropower, wind, and nuclear, up sharply from under 40% just a few years ago. Miners have become some of the most flexible mobile power buyers on the planet, happy to set up shop wherever cheap, otherwise wasted electricity is sitting stranded. And here's the twist reshaping the industry right now. Many of the largest mining operations already have exactly what the AI boom desperately needs: massive power contracts and industrial-scale cooling infrastructure. So as mining rewards keep shrinking on schedule, a growing number of these companies are repurposing that same infrastructure to host AI compute instead, turning themselves into hybrid energy and compute businesses almost overnight. Which brings us to the part of this story that's moving faster than almost anything else in tech right now. Here's a problem you don't think about until it's put in front of you. An AI agent can browse the web, write code, and book you a flight. But it can't open a bank account. It can't pass a credit check. It has no legal identity a bank will recognize. So how does an autonomous AI system pay for the things it needs: API access, compute time, data, without a human manually approving every single transaction? In 2026, the answer that's actually shipping in production is a protocol called X402, built by Coinbase and Cloudflare and now governed under the Linux Foundation with a genuinely striking list of backers: Visa, Mastercard, American Express, Google, Amazon Web Services, Stripe, Shopify, and Anthropic, the company behind the AI model narrating this very video, among more than 20 others. Here's how it works, and it's almost absurdly simple. A server that wants payment sends back a very old, mostly unused piece of the internet's original design: HTTP status code 402, payment required. An AI agent's wallet signs a stablecoin payment, resends the request with that payment attached, and gets what it asked for: no account, no credit card, no human in the loop. The entire exchange takes seconds. And this isn't a pilot program anymore. In its first year alone, the protocol processed well over 100 million of these machine-to-machine payments. Google has built support for it directly into its own agent communication standard, so AI agents from completely different companies can not only talk to each other, but pay each other automatically. There's a second piece to this that matters just as much: using blockchain to timestamp and verify the actual data used to train AI models, creating a tamper-evident record of where training data came from, making it dramatically harder to secretly poison a model with fake or malicious data after the fact. AI models are frequently described as black boxes. You feed something in, a decision comes out, and the reasoning in between isn't always fully visible, even to the people who built the model. Blockchain doesn't solve that mystery, but it offers something almost as valuable: a tamper-proof, time-stamped log of exactly what an AI system did and precisely when it did it. That distinction, not knowing why, but being able to prove what, becomes critical the moment AI starts making decisions in healthcare, finance, or autonomous vehicles, where trust me isn't good enough and accountability can be a matter of life and death. From a classified ad buried in a 1990s newspaper to a $600 million a year payment network run entirely by machines, that's the arc of this technology in 3.5 decades. Blockchain isn't the flashy part of the story anymore. It's becoming the invisible plumbing underneath a more transparent, more automated world, whether or not most people ever notice it's there. But the most important part of that story was never really the code. It's the people who understand it well enough to use it, or question it, on purpose, instead of by accident. That wraps up our two-part deep dive into blockchain. Thanks for sticking with us through both halves. This was a dense one, and we appreciate you seeing it through. If it helped the technology finally click for you, a like goes a long way, and subscribing means you won't miss what we dig into next. And genuinely, drop your ideas in the comments. Half of what we cover on this channel started as a suggestion down there, so if there's a technology, a mystery, or a piece of engineering you want us to take apart next, we want to hear it.